Hello and good morning. Welcome you all for the NPTEL online course on economic operation and control of power systems. Just to summarize, we have learnt about three different topics. The first one is piecewise linear approximation, where we find out the optimal schedule while we carry out different segments for each generators, starting from the lowest lambda minimum to the highest lambda maximum, right? So then we will formulate a table where in the ascending order we will make an entry to each and every row, so that we will get the optimal schedule choosing from the lowest lambda minimum to the highest lambda maximum, right? And the second was about participation factors, right? If there is an optimal schedule which is already been done and there is a sudden change in the load, and what is the share of the load with respect to each generator, such that the new generation with respect to each generator will be also an optimal schedule or the most economical schedule, right? And the third aspect that we have learnt is, let's say there are n number of generators which are connected to a bus, and to that bus there is also a load and a new generator is coming up which has some fuel constraint. Then how do we carry out this operation? So we have understood that the n number of generators can be represented with one single generator, which we call it as a composite generator, right? So then we started lambda, the algorithm what we have designed helps us understand that the lambda is starting from the lambda minimum. Each generator has its own lambda minimum and lambda maximum. We will find out the most minimum lambda minimum among all the lambda minimum, the most maximum lambda maximum among all the lambda maximum, and we will start from lambda minimum, the most minimum lambda, to the most maximum lambda, and while we vary in terms of step, then we will find out the total generation and total fuel cost. And if the tolerance is very less, let's say 1%, then it's reasonably matching with the actual curve. So we will obtain the smooth curve, we will join the points, we will obtain the overall fuel characteristics by connecting the points, and the objective is to ensure that with the help of curve fitting formula we will obtain as smooth curve as possible, so that we will not jump into the non-convex problem. So in today's class we will try to explore further topics. The first topic is the lambda iteration method. See, the solution to the optimal dispatch can be approached by graphical methods also. Plot the incremental cost characteristics of each generator. See, you can see here, this is the incremental cost characteristics, that is df1 by dp1 of the first generator, and incremental cost characteristics which is df2 by dp2 of the second generator, and incremental cost characteristics for the third generator which is df3 by dp3, right? So you can see here, let's say this is the lambda, right? If this is the lambda, then this is the lambda. Corresponding to this lambda, you would get a specific generation from each generator, right? So sum up together, you will get that. Okay. So we have at a specific lambda, let us say, you have three specific generations coming up. You see here, that is a P1, then P2, and there is P3. You see, lambda is already been chosen, and the lambda minimum of the third generator is higher than the lambda which is already chosen. So, but still we need to stick on to that principle that each generation should have its own, will have its own minimum and maximum generation. So, but in this case, to be very honest, the third generator will not be contributing any generation, but because you need to meet out that constraint, you need to operate this particular generator at its minimum power. So all of them put together, you are getting some generation. Let's say your load demand is what, load demand that you are expecting is exactly equal to the sum of the generation, then you can consider that as a right lambda. Let's say if the generation is increased, or if the demand is increased, then you have to accordingly change the lambda such that for the new lambda the total generation will be matching to the load requirement, right. So let us say the generation is increased from this lambda, the total demand is increased from the original PR to PR plus delta PR, just for an example. Then if the demand is increased with this specific generation, you will not be able to meet out this demand, right. So what you have to do, you have to increase the lambda. Once you increase the lambda, let us say you increase the lambda from lambda to lambda plus delta lambda. That means you will have a new lambda, and that will be something like this, let us say for example. So with respect to this incremental cost characteristics curve of each generator, now you can easily identify that the generation will be of each generator will be higher than the previous generation, right, because the generation is increasing. Now the sum of the generation put together will be meeting out to the new increase in demand, such that the constraint, equality constraint, which is sum of the generation is equal to load, will be met, right, and it will inherently ensure that the frequency of operation will be constant, correct. If let us say the demand is decreased from PR to PR minus delta PR, now what you have to do, you have to go in the opposite direction. So decrease the lambda such that the total generation will be again equal to the new change in the load, right. So this is what this approach is all about. Now you can see here with this error curve you can easily understand. Let us say you have chosen an initial lambda of 1, right. Corresponding to that there is an error, it is not an exact lambda. So you will find out the generation with respect to this lambda. So that generation, the sum of the generation put together is greater than the, or whatever, the difference between the sum of the generation and the load is not 0. Then if the error is positive, then you have to get a new lambda. Now the next lambda is lambda 2 and corresponding generation is a new generation. Now here you can see here, earlier the error was positive, now the error is negative. That means now again you change the lambda, go in opposite direction. Now you get a new lambda which is lambda 3. Now again generation is increasing or the error is positive now, right. But this error is lower than the previous error, the first error. So similarly somehow you will reach the final point which is where error is 0. So with so many iterations, right. As you can see here, if the total power output is too low, increase the lambda value, or if too high, decrease the lambda value, that is it. Now this is your algorithm flowchart. Set a lambda, right, and calculate total generation for all the generations from I to 1, I to n, check the inequality constraint. Now for this lambda you should ensure that none of the generation should violate the constraint. If it violates, then you assign, if the generation is coming out to be lower than the minimum, you assign it that to be operating at its minimum point. If it is maximum, more than the maximum capacity, you assign it to be P maximum, right. Then you calculate the error and then you check the tolerance. If error is the modulus of the error, that means the absolute value of the error is less than the tolerance or not. If it is yes, then that's the end, that's an exact lambda. Otherwise you project the lambda, increase the lambda or decrease the lambda accordingly based on the error, and then for the new lambda you again carry out the generation and the steps will be followed exactly as it is, right. So one thing you need to identify is, as an iterative procedure, a stopping criteria must be established, because if you keep exactly 0, it will keep on oscillating and it may not be able to reach, and it may take so many iterations, sometimes it may enter into the infinite loop also. So somehow you should keep some lower threshold as close as possible to 0, need not be 0 exactly, right. So two types of approaches are followed. The first one is total output power is within a specified tolerance of the load demand, right. So there is a total generation minus total load, and that error can be within the specified band, or you can fix the total number of iteration altogether. Okay, let me carry out, let us say 100 iteration, whatever the value it gets converged, so let me fix that. So usually they follow the first approach, right. Now let us take an example to understand this in a better manner. So you have a characteristics, heat characteristics, and here you can see here it is not quadratic expression, it is a polynomial of 3, right. So degree 3. Now for 3 generating units, find the optimum schedule for a 2500 megawatt load demand using the lambda iteration method, right. So you get the ABCD constants, P minimum, P maximum, everything is given to you, and the fuel cost is also given. Now set the value of lambda on the second iteration at 10% above or below the starting value. Depending on the sign of the error, for the remaining iterations, lambda is projected in the figure. I will help you understand. Okay, let us say we are fixing, to start with, lambda is equal to 8, right. So for now already we have fixed lambda is equal to 8, so obtain incremental characteristics, then you because now the differentiation, after differentiation you will get a quadratic expression, right. So each quadratic equation will have 2 roots, right. So here one is negative, another one is positive for each generation, but you should take out negative, I mean you should ignore the negative value, because ultimately if demand is positive, common sense will indicate that generation cannot be negative, right. So you will have to pick up the positive values of each generation, then ensure that this lies within the range of their limits, P minimum to P maximum. Then calculate the error. Error is total demand, which is 2500 megawatt, minus sum of the generations, right, and still the error is positive. That means load is higher compared to the total generations, for which we have calculated using a specific lambda, which is not an optimal lambda for this specific combination of generation, which should be equal to the total load, right. Now you have to increase the lambda. Now let us say I increase by 10%, it will be 8.8. Let us see how it works. Now for the 8.8 you will get a specific P1, P2, P3, and the error is coming out to be negative now. That means somewhere your common sense will clearly indicate lambda will be between the range of 8 to 8.8, right. Now you project the lambda, again you can go for 10% minimum, 8.8 into 0.1, so you can do all these things, but or 0.05, you can take some value, but how to project it? So it is a simple mathematics. Let us say now you have two set of values, that is you have first iteration you have taken lambda is equal to 8 and you have a corresponding error which is positive, right, and in the iteration 2 you have taken 8.8 lambda and you have a error which is negative. That means now you have an understanding with respect to change in lambda, how much is the variation in the error. So with respect to that you can project a new lambda, that is the difference in lambda with respect to the change in error with respect to change in lambda. Indirectly we are doing d lambda by d error, right. So then you add it to the previous lambda, you get a new lambda which is 8.5615, and for this the total generation is coming out to be closer here, you can see here 2510.2, and again you go for the fourth iteration, now it is almost converging 2499.2, and the corresponding generation is P1, P2, P3. So understand the lambda iteration method will first fix the lambda, calculate the generations, find out the error and project the new lambda, and for the new lambda again carry out the total generation P1, P2, P3, and the steps keeps on followed, so that you will ultimately reach a point where error is as close as possible to 0, right. But there is a catch, that if the finding out the initial point is very critical here. No, if you choose a lambda which is not proper optimal lambda, then close to optimal lambda, then it will keep on oscillating. That is one problem in the lambda iteration method. Let us say I will take an example where lambda is equal to 10, instead of choosing lambda is equal to 8, if I have chosen lambda is equal to 10, then you can see here there is too much of oscillation. You can see here the total generation is decreasing and then increasing, right, and then again decreasing. That means error is oscillating basically ultimately, right, and then it is finally coming to the close point of 2500 megawatt, but it is taking 10 iteration. The previous case it was just 4 iteration, right. So this is one of the challenges, choosing how to choose a specific lambda. Now the next approach is economic dispatch using gradient method. Now let's say if the polynomial is like whole number or degrees whole number in the earlier case, so then it would have been, you can follow lambda iteration method, that is fine. And but if let's say the fuel cost characteristics of a specific generator has a function which is having decimal degrees, right, so or a fractional power, and it has even more complicated polynomial expression. So the lambda search technique requires a solution of the generator output for a given incremental cost, and it is possible with a quadratic or piecewise linear function, however hard for complicated functions. The lambda iteration will be very tough. So we need to have a more basic method to solve this problem. The gradient search method uses the principle that the minimum is found by taking steps in downward direction. Now the gradient search method is a better approach in the case of this kind of problems. So you can see here, from any starting point, let's say you have a starting point x of 0, one finds the direction of steepest descent by computing the negative gradient of f at x of 0. So let's say you have total generators 3, that means you have 3 variables p1, p2, p3, and you also have another variable which is lambda, because in a Lagrangian equation you have let's say n number of generators are there, n plus 1 will be the total variables, because 1 is also lambda, right. Now you can see here, now there is a function, this is a general expression. Let's come to the Lagrangian function in the next slide. So let's say there is a general expression function, there is a function which is a dependent on x variable, x is a vector here, right. So you obtain the gradient of this function with respect to each of the variable, right. Gradient means what? It's a slope actually, right, it's a slope, that means it's dy by dx basically. So the partial differential equation of the function with respect to each variable you find out. That means what I am doing here is, you can see, can you see in this picture, it's a 3D diagram. Let's say you say there is a starting point here, there is another starting point here, right, there is another variable here. Now you find out the steepest slope starting at each point for this function. That means if you place let's say you place a ball here, this is ball 1, you place another ball here, ball 2, you place another ball here, this is ball 3. So in a hilly region, if you place a ball will come down based on it will follow the lowest slope, right, the highest slope actually, So if as this slope is more steeper, it would follow that path and finally reach the point, right. So that's what we are finding out. What we are doing is, the function we have to find out the minimum value. So we are finding the negative of the steepest descent such that all of the variables will converge to one specific point where the error is almost 0, close to 0, right. So for this the path could be something like this, and for this the path could be something like this, and for the third variable the path could be something like this, but all of them would converge at this point. So the principle of gradient search method in ED is that the minimum of function f of x can be found by a series of steps. This is called as process of iteration going in the direction of maximum descent or the steepest slope, you can consider. Hence the search should be directed towards negative of the gradient of the function, right. To move in the direction of maximum descent from x of 0, let's say you start from one point, then for the next iteration you need to have a new starting point, new point where it can start, right. So then you have to obtain the next variable, the next iteration value of the same variable. So that is x1 is equal to x0 minus alpha into gradient function which is calculated at the previous starting point x of 0, and here alpha here represents the acceleration factor, how fast you need to reach the destination. You can choose this randomly, let's say 20, 100. So based on that you will, there is a trade off actually. If you jump too fast you may miss out the actual the most maximum point, or if it is too slow it may take a lot of time. So you can choose it optimally. Then where alpha is the scale or the scale acceleration factor that is used to process the convergence of the search method, and the best value of the alpha is obtained by experimentation. It's like an empirical approach where you find out what is a suitable alpha for this specific problem statement. Now this is anyway known to you for economic dispatch problem. What is the objective function? It is to minimize the total cost, right? So which is a total cost is nothing but summation of the individual cost of the specific generator. So and the constraint is summation of generation is equal to total load, right? Now obtain the Lagrangian function. Lagrangian function is total fuel cost plus lambda into the constraint, right? Now you obtain the gradient for this Lagrangian function. Now what is the gradient? This is nothing but dou L by dou P. Now how many generators are there? N generators. So you will have total n plus 1 variable, which I have already told. So that means you need to obtain the partial differential function of the Lagrangian function with respect to each generator as well as with respect to lambda. So you will get this, right? If you do the partial differential equation with respect to Lagrangian function, you will get dou F by 1 by dou P1 minus lambda for dou L by dou P1. Similarly for the other generators also. So ultimately dou L by dou lambda is nothing but P load minus summation of I is equal to 1 to n Pi. Now you obtain the gradient function. Now I will explain you the steps, how we can solve this problem with the help of gradient approach. Now in the lambda iteration approach, what we did, we chose a specific lambda for which we calculated the generation. Here it's the opposite way. What we are doing, we are taking out, we are assuming some generations, random generation value for each generator, such that the total generation will be equal to total load. Now you have anyway found out the generation, obtain lambda for each generator, for the specific generator. That means obtain dou Fi by of that specific generator with respect to dou Pi, right, at Pi 0, and you do this for all the generators. That means obtain lambda for the chosen power for all the generators, right, and compute the initial average incremental cost. Because this is not the optimal value, the lambda of each generator will be different. So obtain the average now. So ultimately we need to get a point where lambda of each generator will be equal to the average value, right. In the beginning, the lambda of each generator may not be equal to the average. So then compute gradient of Lagrangian function, right. So what is the gradient of Lagrangian function? If you see here, dou F1 by dou P1 minus lambda. That means what is this? Let us say this is the first iteration I am speaking, lambda 1 of 0, lambda 1 of 0. That means lambda 1 represents lambda of the first generator at the 0th iteration minus lambda average of 0 at the 0th iteration. What is the total average? That is what we are doing indirectly. Now if this is 0, then that is the final point. Now we have come to the average, we have come to the optimal point. So if that error is not 0, that means we need to do the next iteration. We obtain the average and check out whether this error is less than the tolerance limit or not, and if it is not the case, then update the value of xi. That means obtain new variables. What are the new variables? New generation basically here. So that means the generation value of each generator is updated, and that is based on the gradient expression. Xi is equal to, for the next generation, the value is the previous generation minus the steepest descent, alpha into gradient of L, right, and then go to step 4. Then ultimately you will get the point where you will get the error as close as possible to 0. Now let us take a problem to understand it in a better way. Solve the economic dispatch problem for a total load of 800 megawatt, right. Using these generator cost functions, write a Matlab program to also do the same. And I can suggest you also can carry out a simulation or Matlab coding, C coding, and to have an experience or exposure how this problem can be used using a computer program, right. So lambda iteration also can be tried out, and this can also, right. gradient approach. Now anyway, you have the fuel characteristics for each generator. Choose a alpha, then let us say it could be 100, and choose some generation for each initial generation value for each generator. For the first generator I have chosen 300 megawatt, second generation generator it could be 200 megawatt, and third generator it is 300 megawatt. All of them put together it is 800 megawatt, right. Lambda is initially set to the average of the incremental cost of the generator at their starting generator values. Obtain lambda for each chosen value of generator, and then obtain the average. So we are doing average, right, and that is coming out to be 28.27. Now increase for the next iteration, check whether the lambda is same as the lambda average. If that is not the case, then ultimately you get the new lambdas. You follow the same steps which I have asked you to follow, then ultimately you would get this set of results. But you can see that there is no convergence to a solution, because the fuel cost, you can see here, ultimately you get the generator values and corresponding fuel cost. The fuel cost is not converging. You can see here fuel cost is keep on changing, right, it is not constant, because you have to choose the right acceleration factor, otherwise I told then it could lead to wrong values. So then a simple variation can give us a better solution. So what is that? Realize that one of the generator is always dependent variable and remove it from the problem. Now earlier there were 3 generators. Now what we are doing is, anyway sum of the generation of 3 generators should be equal to the total load, or the third generator let us consider it to be a dependent variable, right. So P3 is nothing but total demand minus P1 minus P2, this is also same, right. So now then total cost function becomes, cost function is nothing but the cost function of the first generator, cost function of the second generator, and the cost function of third generator, which is again dependent on cost function of 2 generators, right. Now this function stands by itself as a function of 2 variables with no load generation balance constraint. Now we are just removing that constraint, another constraint, which is summation of generation is equal to total load, because that has been already taken care by this expression. Now obtain the cost. Now the cost can be minimized by gradient method as follows. Now dc by dp1 by dc by dp2, because you now have only 2 variables, you have removed 2 other variables, one is lambda and p3, you have removed them, right. Now this is nothing but df1 by dp1 minus df3 by dp1 and df2 by dp2 minus df3 by dp2. Note that the gradient goes to 0 when the incremental cost at generator 3 is equal to that of generators 1 and 2, obviously. Now a simple variation, the gradient steps are performed similar to the previous case. X of 1, the new update will be the previous minus the alpha into gradient of C, right, where x is equal to just 2 variables now. Earlier x was P1, P2, P3 and lambda. And rework the previous problem with the reduced constraint, reduced gradient. Now you will get gradient of C is nothing but these values, and alpha is set to 20 now. Now if you solve this problem by using a Matlab program, then you can find out that earlier case the fuel costs were not converging, you can see here, now it is converging, you get the same value. That means the generators combination is almost in an optimal manner. Now there is another important method, which is Newton's method, which is even faster compared to the modified gradient method, right. Now the solution process can be taken one step further. Observe that the aim is to always drive the gradient to 0. Now the goal is to make the gradient as close as possible to 0, right. Now since this is just a vector function, Newton's method finds a correction that exactly drives the gradient to 0. Ultimately what we are doing, we are finding that correction minus alpha into gradient of x, that is nothing but a correction. So we need to find out that optimum correction to which the new variable will be taking us or leading us to the 0 value, right. So that is what Newton method is trying to solve. First we will take help of Taylor's series of expansion. Let us say there is a function g of x that need to be driven to 0. Now g of x plus delta x is equal to g of x plus g dash of x into delta x, and that should be is equal to 0, right. This is a basic Taylor series that you can learn from your basic mathematics. So, and the objective function g of x is defined as g of x is equal to g1 of the total variables and up to, it is a vector where you have the function with respect to each variable, and then you get this vector. Now obtain the Jacobian. G dash of x is nothing but dou g1 by dou x1, that means obtain partial differential equation for each of the function with respect to each of the variable, function with respect to each of the variable, and the adjustment at each iteration step is delta x is equal to minus Jacobian inverse into g of x. How do you get this? Just from Taylor series, you can see here g of x plus g dash of x into delta x is equal to 0, right. Obtain delta x from this, that is minus g dash of x whole inverse into g of x, right. If the function g is the gradient vector gradient of L of x, then delta x is equal to minus d by dx of gradient of Lx inverse into gradient of L, right. Now anyway, we have this Lagrangian function. Obtain partial differential function of this gradient of this Lagrangian function with respect to each variable, that means d square L by dx1 square. In the first row you have d square L by dx1 dx2 and up to, and then you will get d square L by dx1 into dxn. Ultimately here you have last entry d square L by dxn. Solve the previous economic dispatch problem example using Newton's method. Also write a Matlab program for the same. You can also try out Newton's method to have the solution by using Matlab program, right. So the gradient function is the same as the previous example. Let the initial value of lambda be equal to 0 and obtain the Hessian matrix. Hessian matrix is nothing but the gradient partial differential function of the gradient function. Then you get d square f by dp1 square as the first row entry, and everything will be 0 except the last one, which is minus 1. So nothing, it is very simple. You can just obtain d square L by dp1 square, then you will get this one, and d square L by dp1 into dp2, then you will get 0. Similarly you obtain for all the entries. Now the initial generation values are also the same as that of the example 1. Now with this approach you can see that starting from lambda is equal to 0, in the next iteration itself, the second iteration itself, you are getting the value which is almost converged, and you are just verifying with the other few steps. So Newton's method is the most fast method where you get the solution. Even in the case of those problems where you have complicated polynomial where there is fraction involved, right. So the advantage is the quick convergence to a solution as compared to the gradient method. That's it. Thank you very much.